In this video, we're going to talk about gas pressure. This goes with Unit 3, Objective 1. We're going to talk about what causes pressure and some other things that might affect pressure. So we're going to get out our Cornell paper. This is going to look a little different today because I'm doing it a little bit different. Okay, so here's our Cornell paper. Make sure you start by putting your name, class period, and date on there. Our objective is 3.1. My 1 disappeared. There we go. And that's going to be talking about gas pressure. Whoops. Okay, so that's a problem. We can do this. Okay. Our essential question has two parts. We're going to be talking about what causes gas pressure, and then we're also going to be talking about what things affect gas pressure. When we look at gas pressure, we start off by thinking about it in terms of physics. In physics, when we talk about pressure, we're talking about a force per unit area. Let me move the mouse out of the way there. So a force is caused when objects push each other or pull on each other, and the area is like how much space it takes up. So you can have a lot of force in a little area, and that'll be a lot of pressure, or you can have a little bit of force, but in a very tiny amount of area, and you'll still have a lot of pressure. When we talk about gas particles in chemistry class, what we're looking at is those particles bumping into each other. That's where the force comes from. Now, we only talk about the ones hitting the container, and the reason for that is that when we talk about the gas as a whole, all those particles bumping into each other, those forces are equal and opposite according to Newton's third law, and when we add them all up to talk about the whole gas, those cancel out. So we don't consider the ones in the container because they cancel out. Okay? So when we talk about pressure in here, that's what we're going to be talking about, is the particles hitting the container. Now there's a bunch of different units that we use for gas pressure, so let's take a look at some of those. The first one we'll talk about is the Newton per meter squared. That is the SI unit. Newtons for force, meter squared for area, so that's literally Newton's force per area in that one. In chemistry, we don't really use that one. We use atmospheres pretty commonly. Atmospheres is abbreviated ATM. Some other units we use are the bar, which is abbreviated the bar. You might have also heard millibars. Millibars is a fairly common unit of pressure. There's also the PSI. That's a P there. It's partially covered up. Pounds per square inch. If you've ever had to put air in your car tires, then you've probably heard of pounds per square inch. That's a pretty common American pressure unit. There's also millimeters of mercury. Sometimes we use inches of mercury also, but Hg is for mercury and mm is for millimeters. Torr is actually the same thing as a millimeter mercury, so those are used kind of interchangeably there, but only between those two. And then the last one on our list is called the kilopascal. The kilopascal is another SI unit that we use for pressure also. So those are some of the units of pressure. Okay, so the next thing we're going to talk about is the things that affect pressure. And so in order to talk about that a little bit better, we're going to take a look at a simulator. Hopefully this works out okay. All right, here's our simulator. Okay, so let's take a look at what we've got going on. We've got a guy over here holding the side of this container, and we've got a thermometer up here measuring the temperature. It's kind of low right now. And we've got, this is our pressure gauge. Atmospheres are not a very big unit. The pressure in the classroom and in your house is probably right around 1 atmosphere. On a high pressure day, it might be 1.0 something, and on a low pressure day, it might be 0.99 something, but it's always around 1. Down here, I can add or remove heat, and this little gas pump, bike pump looking thing here lets me add or remove particles. So if you take a minute and you think about what things are affecting the pressure, let's take a look at these particles here. You see them bouncing around in here. They're bouncing off of each other, and they're bouncing off of the walls of the container. We don't really care about them bouncing off of each other because, again, those forces kind of cancel out when we add them all together for every particle in here. And it's like a bunch of little pool balls bouncing around on a pool table. They just bounce off and go in some other direction. So if you look at like an edge here and you pay attention to how often particles are bumping into it, that's what we're measuring when we think about the pressure. We're looking at how often particles bump into the container. So let's think about some things that might affect how often things bump into the container? Well, to be honest, there are these three things that we have control over here. So what do you think happens if I add some more particles to the container? If there are more particles in the container, how is that going to change how often particles are bumping into the wall? Well, let's add some and see. All right, I added some more particles. Should I add some more? All right, now there's a bunch more particles. Now if you take a look at the wall here, maybe over here where we were looking before, do you see since there are more particles bumping into each other, or not into each other, into the wall. They are bumping into each other more also, but so that means that when we add more particles, we end up with more pressure, okay? Well, let's think about what would happen to the pressure if I changed the temperature. Now, remember, the temperature we learned in Unit 2, temperature affects the speed of the particles. So the higher the temperature, the faster those particles are going to be moving, and the lower the temperature, the slower those particles are going. So let's look. Here's my pressure now. It went up since I added those particles. What would happen if I cooled them off? Look, there's some ice. They're cooling off. You see them slowing down. And now that those particles are moving slower, the temperature went down. Now look at how often they're bumping into the side. They're not moving as fast. The pressure has gone down because they're not bumping into the container quite as much as they used to be, as you can see in the number here in the pressure gauge. So temperature affects the pressure. The number of particles affects the pressure. The last thing is going to be the volume here. So this guy over here, he can make this a bigger container or a smaller container. And so what do you think is going to happen if I make it bigger or smaller? In fact, I'm going to hold the temperature constant. Okay, what's going to happen if I make it bigger or smaller? Well, if I make it smaller, now there's less room for those particles to be bumping around in there. Lovely bell. There's less room for those particles to be bumping around in there, and so they have to bump into the wall a little bit more often. Imagine you were at basketball practice in the gym, and your coach told you to run from one side of the court to the other side of the court. It would be easier for you to hit each side of the court faster if it were a smaller court or a smaller distance. So these particles, they don't have nearly as far to travel, so they can bump into those walls even faster when they're closer together. Likewise, if we make it even bigger, now they have to go even further to be able to run into that other wall, and so the pressure goes down quite a bit more. So let's sum that up in some notes. Let's see if I can make that go away. There we go. Okay, so what I'm going to do is I'm going to go to the back of the next page here. So we're just looking at a simulator to show us those particles so we could think about what was going to happen and what changed. And now we'll talk about it. So first we'll start off with, let's see, where's my mark there? Can't find it. Eventually I'll come across, there it is. Okay, so the factors affecting pressure. And remember, when we're trying to affect pressure, what we're trying to do is we're trying to determine what causes the number of collisions to increase or decrease. And we talked about three things. I think temperature is going to come up first here, and that is the speed of the particles. So if we increase the temperature or we decrease the temperature, we're changing how fast the particles go, and that's going to make them bump into the signs more or less because, well, they're going faster or slower. So think about it. If you're in a room and you have to hit the walls a certain number of times a minute, if you ran faster, you could hit the walls more times per minute. Okay, so that would be an increase in pressure. The second one is the number of particles. We saw that one. That was pretty cool. The more particles you have, the more collisions there are. Imagine if you had this classroom here and it was full of people and we were counting how often people ran into the walls. Well, if we put more people in the wall, we'd have more people bumping into the walls. That makes sense. Okay. Last one here is the volume. My V disappeared. The volume. We're talking about the space that it takes, the space that the particles have to move here. And we saw in there that when they have less space to move, then they have fewer collisions or more collisions, and when they have more space, they have less collisions. So maybe you noticed that all of these here are kind of the same. Let me pick a different color here. So we've got faster and more, more particles and more. And then we have this last one here that's backwards. Let me make it a different color since it's so backwards. Green maybe. Then we have more and less. So we've got some relationships there. We just think about what the particles are doing. So I hope you enjoyed my introduction to gas pressure. We'll talk some more about what those gas particles are doing in some later objectives. Thanks for watching.